Hello and a very warm welcome to you. In this video, I'm going to mirror a video by FE Dogma. He's given me permission to do so, and I can recommend his channel to you. I'll put a link maybe in the video here and also in the description. It's well worth checking out some of his videos. He's got some really good debunks of things that flat earthers have done. Several of our old favourites, Mr. Riley, Black Swan, Ranty and Phuket Word. The video today concerns one that was made by Ranty, and FE Dogma does a wonderful job of showing that Ranty gets everything wrong in his video, as is usually the case. So I'm going to play that video, and then I'm going to look at some of one of my older observations, because it's that sort of observation that Ranty was attempting to explain. So enjoy FE Dogma's video, and if you do, don't forget to pop along to his channel. He's got 302 subscribers, and I'm sure we can get that up considerably.
So I'm going to take a look at this video by Ranty, and it is titled "Sinking Experiment Crushes the Globe Rhetoric for Observations." So this is Ranty's setup. He's taken a photograph of a paint can and a ruler through a sugar water solution, and in the middle of the fish tank he has a cone-shaped object. Now, I'm really not certain why Ranty didn't compare a sugar water solution to plain water, but this was his setup. So to the existing water on the left, he added a mixture of 1,450 milliliters of sugar with 1.5 liters of water. And then for the photograph on the right, he added an additional 2,000 milliliters of sugar with 1.5 liter of water. Of course, there is increasing density at the bottom of the fish tank, and at one point Ranty did shine a laser light through it. And when you compare it to a straight line, you can clearly see that the laser light is bending downward. And of course, we know that downward bending light is the cause of looming. Looming is also a very simple concept to understand. So here we have an observer looking at a sailboat off in the distance with no refraction. So the light travels in a straight line. Now I've added a light path that is refracted downward. So this light path enters the observer's eyes at a higher angle. So to the observer, the sailboat appears higher than it actually is. But Ranty's making the opposite claim, that the object is actually lower than it really is. So let's take a listen to Ranty.
These two images were taken in different density gradients. The first image on the left was taken after adding 1,450 ml of sugar and 1.5 litres of water to the water already in the fish tank. The second image on the right was taken after an additional 2,000 ml of sugar and 1.5 litres of water were added to the fish tank. You can see that the pot I placed in the tank lines up pretty well in both images, and the cumulative effects of the density gradients have not had enough length to make the object move its visual position. However, when you look at the tin of paint in the right-hand image in the background, you can see that it is sunk in relative position to the pot. This proves that on a flat plane with a density gradient, distant objects will fall out of their expected positions and appear lower in the image. This very simple demonstration has proved Miles Davis and co. wrong, and proven that sinking is indeed a very real reason as to why we see things the way we do, over our wonderfully flat plane. I've been Ranty Flat Earth, and I'll see you all in the next one.
So Ranty aligned the top of the cones in both photographs. And when a straight line is drawn across the top of the can on the left, it does appear that the can on the right has sunk. The top is definitely lower. But let's take a look at a few more things in these photographs. Now, when I draw a line across the top of the number 5 in both of these photographs, we really don't see any change at all. There also doesn't appear to be any change at the bottom of the label on the paint can. But what do we have here? That mark on the piece of paper is definitely higher on the right, so that is a definite case of looming. And is this the number 6 up here in the right photograph? I mean, that number is blurry in both of the photographs, but I certainly don't see it in this area. So here's another case of looming. The bottom of the paper is also higher on the right. This black line on the left over here is also higher on the right. And we see the same thing with this dark band to the right of the cone, because over here in the right photograph, it is certainly higher too. So you got to ask the question, I mean, there's clearly real evidence of looming here, and yet in the middle we have one example of sinking. So why is this? Now, I don't have the answer because I did not do the experiment. But one thing might be is that Ranty might have just arbitrarily used the top of these cones for the alignment. So let's try something a little bit different. So what I did is took a cutout of the photograph on the right and I moved it up slightly so that the top rim of the paint can are now in alignment. Now, of course, the cone on the right is also a little bit higher, so it has loomed up. And look at this. Now everything is loomed upward. And this is exactly what we would expect to see when we have a density gradient that is bending light downward. So all I can say is thank you, Ranty, for more globe evidence.
So the reason that Ranty is quite keen to be able to demonstrate sinking is because I've published a number of observations. The best one is this one. It's taken quite a while ago now, a couple of years ago. I was on a hill called Traprain Law in Scotland. It's in East Lothian if you want to track it down. And Traprain Law is 221 metres above sea level at its summit. There's a survey point there with a precise height measurement of 221 metres. Actually, my camera was a metre or a metre and a half higher up, but that actually makes the observation even more dramatic, as we'll see in a moment. In the relative foreground of this picture, you can see a tower on another hill. The hill is called Byers Hill, and the tower is the Hopetoun Monument. And it is 210 metres above sea level at the top. If you take the combined height of the tower, add it to the height of the hill, you get 210 metres. What that means is that my camera is basically at the same height as the monument above sea level. So if the Earth was actually a flat plane, as I look out past the monument, every object that is 210 metres tall, or taller than 210 metres, should appear above the red dotted line drawn across the screen. Yet we have 3 mountains in the distance, all of which appear below that red dotted line. Now I'll show you a couple of pictures in a moment that illustrate why this is the case. It's important to note that I could have engineered this, or even on a flat Earth, to make these mountains appear below the line if I had had my camera below, probably considerably below 210 metres. But my camera was most definitely above 210 metres, and that should make these mountains drop even lower. in the picture. So let's illustrate that point with a couple of real-life demonstrations of how objects behave on a flat surface. So this is a demonstration to show why an object or the mountains in the distance should appear above the line drawn across from the top of the Hopeton Monument. So this corridor is around 9 meters long, and I've placed 5 pairs of soda cans at various distances from the camera at this end of the corridor. 2 cans stacked on top of each other, with the camera at the same height as the top of the lower can. And we have a red line, dotted line drawn across the screen. And you'll see that all of the cans, as we go back into the distance, the top of the lower can is always level with that line. The cans are all the same height, and the top of that can, of the subsequent cans, is always at the same elevation in the image. The floor is level, demonstrated by a laser here, which hits the wall at the far end, the same height it is above the floor at this end, and the laser is actually mounted within a spirit level, which shows that the floor is level at that point, and the laser is level at that point. So we have a level, flat floor, the cans on the floor, and although the height at the top of the 2 cans drops down as we go into the distance, and the bottom of the lower can rises up as we go into the distance, the top of the lower can, the bottom of the upper can never can cross this line at eye level. So I've often used this demonstration to demonstrate the point I'm making about the mountains should appear above the red dotted line in the photograph. So what I've done here is place my camera at the same height as the darker of the 2 cans in the little stacks of 2 soda cans on this flat and level floor. With the camera at this height, the lower can can never appear above the red dotted line drawn across the screen. The top of that can is always on the line, no matter how far away the can is. The upper can of the combined stack of the 2 cans is of course taller than this darker can in the foreground, and it always appears, the top of that can always appears above the red line. And hopefully you can see that even if these cans were to continue further and further into the distance, the upper can would get shorter and shorter but remain above the line, and the lower can would get shorter and shorter, but the top of it would still remain below the line. In fact, the whole can would remain below the line. Now, of course, this is done over about a 9-meter stretch of flat level flooring, established as flat and level with a laser attached to a spirit level. Of course, it would be nice to be able to do a 100-kilometer plus test on a flat and level surface with objects of known height or known elevation. But there isn't anywhere that I'm aware of on Earth where we have a flat level surface for over 100 kilometers. The best I could do locally to extend the distance was to go to a local indoor running track. And here we have some hurdles placed on the flat and level floor. The hurdle in the foreground here is about 50 meters from the camera. And I've zoomed in a little bit to make it clearer to see. The two hurdles next to it are about 10 meters further away. And the hurdles in the distance, one tall one and one the same height as the hurdles in the foreground, are about, well, they're over 80 meters away. And we can see that the rule of perspective and eye level holds true as we extend the distance from just 9 meters or so out to nearly 90 meters. And there's no reason to suppose that if we were to extend this out to a further distance, even 100 kilometers, 125 or 135 kilometers, there's no reason to think that this rule would stop working. However, it is possible that atmospheric conditions might alter the observation a little. And this is what flat earthers like Ranty are trying to claim. Now, I'd quickly like to show you another picture that I took at the running track. And here I've placed my camera slightly above the hurdle in the foreground. So this more accurately mimics where my camera was in the Stooping law, observation of the mountains and the monument. With my camera above the object in the near foreground, it doesn't have the effect of making objects in the distance, tall objects in the distance, lower their elevation in the picture. It causes them to be raised up further in the distance. So even the two hurdles here in the foreground that are the same height as the first hurdle appear above it. And the tall hurdle and the shorter hurdle in the distance are also raised up in the picture. Perhaps if I put a second line across the screen, you can see what I mean. So I hope the monument line would be the lower of these two red lines. And objects in the distance that are even the same height as the Hopeton monument should appear above the line if the Earth is flat. So I think we can see that the claim I made that on a flat and level surface, if the Earth was flat, we should see these mountains appearing above the red line. And they don't. And I've challenged flat earthers for years to provide an explanation based on flat Earth for this observation and numerous others. Ranty seems to be opting for the possibility that sinking due to atmospheric refraction might explain observations like this. Of course, his demonstration of sinking using his pot and his paint can and so on is a complete and utter failure, as FE Dogma showed us. But sinking due to atmospheric refraction does occur. There are references on the internet, I may link to one of them, that describe the phenomenon. However, it requires particular conditions to be present in the atmosphere, and it tends to be a relatively small effect. In order for Ben Narnain, a 1,000 meter mountain, over 1,000 meters tall at the peak, to fall this far below the line, with my camera higher than the Hopeton Monument, higher than the line, would require sinking of over 1,000 meters. And even over a distance of 137 kilometers, the conditions required to achieve that simply don't exist. However, I know the weather conditions on the day in question. It was 8 degrees centigrade on Traprain Law, where my camera was. It was 8 degrees centigrade at the foot of Ben Lomond and at the foot of Ben Eam. And it was 4 degrees centigrade at the top of Ben Lomond. Ben Eam's a little further away, but there's no reason to think that it was much different to the temperature at the top of Ben Lomond. All three of these mountains are in exactly the position one would predict on a spherical Earth, with standard atmospheric refraction occurring, not sinking, not exaggerated looming, but just standard atmospheric refraction causing a small-ish amount of looming. And we can see that in this picture. Here I've modelled or used Walter Bislin's model to model the observation on a flat Earth and on a spherical Earth. The flat Earth model, with the red and yellow marker here to indicate the monument height and hill height combined, a red dotted line drawn across, and Ben Lomond, Ben Nunnain and Ben Eam represented by these little grey shapes to represent mountains. And this is what the flat Earth modelling predicts. The spherical Earth model predicts what we see on the right-hand side at the bottom of the screen, with Ben Lomond just below the line, Ben Nunnain a bit more below the line, and Ben Eam somewhere in between the two. And this is with standard atmospheric refraction applied. Without any refraction at all, these mountains appear yet lower below the line. And if you apply greater than standard atmospheric refraction, Ben Lomond starts to appear above the line. Ben Eam and Ben Nunnain remain below the line. The spherical Earth model matches the real-world observation. A flat Earth model does not. What flat Earthers need to do is to come up with an explanation which effectively means some sort of a model, something that can be defined and described reasonably accurately, that shows how this observation could be produced on a flat Earth. Of course, this isn't the only one of my observations that flat Earthers can't explain, so I'll leave you with this photo and show you a few of the others. Thanks very much for watching, and I hope to see you again soon.